musicologist and mathematician Dmitri Tymoczko, who will speak about vectors in music. I just want to get a personal note. I'm really pleased. I just found out from Wikipedia that Dmitri is the son of my great hero, one of the great pioneers of experimental mathematics, way before experimental mathematics was even recognized, the great philosopher Tymoczko, who predicted that one day mathematics will become quasi-empirical. So we go one step beyond. So it's a very great pleasure to have Dmitri.
Okay, thank you everybody. Today I'm just gonna give an introduction to a bunch of the work that I have been doing over many years now, and I'm going to sort of go back in time. So I'm going to start with some more recent ideas. How many of you read music? Okay, good. The majority. For those of you who don't read music, you're going to see some notation. And the thing basically to realize is that musical notation is a graph, a two-dimensional graph, and pitch, which is the respect in which those notes are all different. Pitch goes on the y-axis, and time goes on the x-axis. So if you don't read music, you're not going to get some of the specifics of what I'm talking about, but hopefully this will help you just understand where I'm coming from. There's basically a mapping between positions here on the y-axis and the white notes of the keyboard, as I tried to sort of show on this. Okay, and I'm going to try to go through all this quickly, and we'll have time for questions after, but if I say something that's wrong or very confusing, or you really feel like you need to interrupt, you can interrupt, and we'll see how that goes. Okay, so informal musical talk, the kind of talk that you engage in with very young music students, the things that musicians talk about all the time, contains a number of terms like note and chord type that all refer to what you could think of as a point in an abstract space of musical possibilities. A note is a location. A chord is also a location. At a more abstract level, the idea of a major chord is an abstract location, a kind of equivalence class, if you will. There are also a collection of terms like interval, chord progression, and voice leading that seem to refer to something more like vectors, understood in the high school geometry way as ways of getting from one point in the space to another. So there's a variety of ways that we can think of these, but informally, these terms are not points, but rather transitions from one point to another. And in some ways, in some situations, it is really easy to figure out how to cash out this metaphor of points and vectors. Okay, so when we talk about notes, C4, this number gives the octave, so C4 is a name for middle C, and E4 is the name for the E above it. And the points in this space are all called notes, and the vectors are all called intervals. So the name for this vector is the ascending major third. And basically the space of notes and intervals is one-dimensional real affine space. And it all just works out beautifully, the translation between points, vectors, notes, intervals, and so on. In other cases, it is not at all obvious how to cash out this metaphor of points and locations and vectors and transformations between these locations. In particular, we musicians like to talk about something called voice leading, which roughly speaking is a way of getting from one chord to another chord. And basically a lot of my work over the last decade or so has been concerned with figuring out how to make this metaphor of musical vectors quite precise. And it turns out that voice leadings are going to correspond to vectors in orbifolds. But the problem here is really figuring out how to characterize the space correctly and how to characterize the what the points are and just how these more complicated abstract musical spaces work. Before I get into that, so basically this whole talk is going to go the long way around and eventually end up with the full mathematical translation. Before we get there, I want to start with a little bit of history because I think this is really interesting. Over the last 30 or 40 years, music theorists worked really, really hard to come up with a formal theory of musical vectors. And I think it's fair to say that these efforts really had only limited successes. And I, as I have thought more and more about these subjects, find it more and more fascinating to think about what the problem was. And one interesting way in which musicians had a problem is that they didn't try to explain which musical vectors were fundamental to composition and analysis. And there was probably the most influential music theorist of the past 50 years is a teacher of mine named David Lewin, and he had a mathematical taste for abstraction and wanted to remain extremely neutral about what musical vectors might be. This is a little bit like category theory, is his conception of vectors. It's almost totally neutral about what points and what musical arrows could be. And in a way that I think is fascinating, in his quest for the ultimate philosophically general conception of musical vectors, Lewin ended up promulgating formal tools that completely inadvertently prevented people from adequately formalizing a central class of musical vectors. And so one of the biggest problems I've had in my life as after graduate school is that I have, at every turn, when I've been trying to present the ideas I'm talking about today, I have been met with resistance by people working in this tradition that David Lewin started, who are convinced that I am talking nonsense because the ideas I have just don't fit into this sort of very general conception of musical vectors. And I realize this is a little bit inside baseball for you mathematicians who are not involved in formal discourse on music theory, but there's a kind of tremendous lesson here. It's almost like a play or something about how the quest for a certain kind of generality can lead you astray.
So it's too abstract.
Well, it's not just too abstract. Let me give you an example so you'll have a sense of what I'm talking about. One of the most basic music theoretical activities is to ignore octaves. So instead of thinking of notes as points on a piano keyboard, which is a line that goes from top to bottom, the idea is to do justice to the periodicity inherent in our perception of pitch and in the design of our musical instruments. You know, if you look at this thing, you notice that there's a pattern, right? And the black notes come in a group of 3, and then a group of 2, and then a group of 3, and then a group of 2. And that reflects the really profound fact of octave equivalence, which is as you go up the scale, say do, re, mi, fa, sol, la, ti, you eventually get, via what I call Maria's theorem, back to do, right? And so the way you represent that is you wrap the line around into a circle, just like the clock, where you can imagine wrapping time, which is linear, into time of day, which is periodic, and since you're mathematicians, you don't need to be told any more about this. Now, the amazing thing is that for 50 or 60 years, traditional music theorists recognized only one way in which you could move from one point to another on the circle. So they would ignore octaves, and then essentially they would think of the circle as a group, okay? And so if you were at this point in the circle, C, and you wanted to move, say, to this point on the circle, according to the official, supposedly super general conception of musical vectors, that was all there was to say. You started at C and you ended at E. And there just wasn't any other sort of fact, there wasn't any fact of the matter about how you got there or where you went. Okay? And this actually was quite disastrous because there are a lot of ways to get from C to E. You could go C to E, or you could go C to E. You know, and these are all very different. For instance, Beethoven's Fifth Symphony is all about going, right? G, 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 E flat, and not G, 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 E flat, or anything like that. It's that one, the one that goes down by 4, not the one that goes up by 16. And there was literally no way to talk about that in musical discourse. And the reasons why are actually quite fascinating to me. One reason is that the founders of modern American music theory wrote a very specific kind of music called 12-tone music, which is almost unique in all the music in the world in the extent to which it asks us to ignore the specific location of notes in musical space. So these are two themes from the first 12-tone piece by Arnold Schoenberg, a wonderful piece, the Suite Opus 25. And here's one melody, E, F, G, D flat, that's all you need to know. And here's the melody of another movement, E, F, G, D flat. And these notes are all in different octaves. And the idea of this style is you're supposed to hear these as representations of the same musical pattern. And this is totally unlike any other kind of musical style that I know about. For instance, Mary had a little lamb is not the same as You know, you can't just move things around like that. In almost any other kind of music, you destroy the melody by shifting individual notes. Sure, you can shift the whole melody up and down, but you can't shift the individual notes. So what's fascinating is these people who wrote this very strange kind of music imposed this way of thinking about music onto their quest for a general theory of musical vectors. Another thing is a lot of these theorists wanted to uncover isomorphisms between the kinds of structures that could be embodied in pitch and those that could be embodied in other dimensions, in particular rhythm. And, quite naturally, the quest for isomorphisms is easier to satisfy the more abstractly you conceive of musical vectors. And this is particularly true in pitch and rhythm, where, according to the, in my opinion, bad old way of thinking about musical vectors, pitch and rhythm are virtually isomorphic. But if you have a more accurate, if you have a better sense of musical vectors, then these two domains seem to be non-isomorphic because you cannot go backwards in time. Anyway, there's also cultural stories about how these theorists were just, because of their upbringing, they were very comfortable with discrete mathematics and group theory and had little exposure to geometry and so on. Okay, so now we get to some actual sort of positive, non-historical information. When I left graduate school, I ended up going back to the drawing board and trying to rethink how musicians and music theorists should conceive of musical vectors, and I came up with something that I called a path in pitch class space, which shows how one point on the circle, or note when we ignore octaves, moves to another point on the circle, and they are equivalent to English language phrases like G, whatever octave it is in, moves up by 8 semitones to E flat, which is not what Beethoven's Fifth Symphony does, and G, whatever octave it is in, moves down by 4 semitones to E flat, which is what Beethoven's Fifth Symphony does. Now, from a mathematical point of view, these are probably most naturally represented as vectors in the tangent space of the circle. In musical cases, we can also think about these things as unidirectional paths on the circle, since the space is basically flat. So there's sort of two directions that you can go here. One leads toward vectors and differential geometry in the tangent space, and the other is about paths in the space and leads toward things like homotopy theory and working that out on orbifolds. And they both basically work because musical space is a pretty simple space. There isn't an analog of curvature in most of the cases that you have to deal with. So here's how you can picture them. These are two separate ways of getting from G to E flat, right? One goes up and goes up by 8, 2/3 of the way around the circle. The other goes down by 4 and that's the one that Beethoven uses in the Fifth Symphony. This is very, very, very simple stuff, of course, but it was, trust me, an enormous effort to try to get music theorists to even conceive of the idea that on this circular space there could be multiple ways of getting between the same points. Okay, so once we have this simple notion of an interval in pitch class space, which can be represented on the keyboard in many different ways. So G going down 4 is the same as, or the same as, but it's different from, right? So it's just an equivalence class of possible pairs of notes on the piano keyboard. It's really not a complicated idea. Once we have this, we can define a notion of a voice leading, and we can actually formalize this all-important informal concept that musicians talk about all the time. A voice leading is just a collection, multi-set, of these paths in pitch class space. And what it does is it shows how the notes of one chord move to the notes of the other. So a voice leading, this is my definition, tells you that you can move from, say, the C major chord to the F major chord by keeping the roots, keeping C constant, moving E up by semitone, 1 piano key, and moving G up by 2 piano keys. Okay? And so we can represent it as a multi-set like this. C moves by 0, E moves by positive 1, G moves by 2. That's a recipe for how to get between two different places in musical space. Every composer, every elementary music student knows this recipe. If you say, play a C major chord, they will play this, and you say, now play an F major chord, they will play exactly this voice leading. And this voice leading can be instantiated by many different patterns on the piano. I wish this were louder, I apologize. But not every way of moving from C major to F major is a representation of this specific path of motion, this specific voice leading. Okay? So there's one way to represent them. That's probably the most mathematically perspicacious way. The way I do it in my book is a little bit different. I represent the starting point, the point-like nature of our starting place, the C major chord. The vector is up here, and here's the destination, which is, of course, redundant, but to a musician, this kind of redundancy is useful because you don't have to calculate. Oh, you see immediately, I'm going from C major to F major. So this just says C, whatever octave it's in, moves by 0 to C. E, whatever octave it's in, moves up by 1 to F. G, whatever octave it's in, moves up by 2 to A. The punchline is these really are going to be vectors in higher dimensional configuration spaces that are singular, and hence this is a vector or in an orbifold or a class of paths in the orbifold. Usually I leave out these numbers when notes are moving by the shortest possible distance, which they typically are, so it's just a little bit more legible to see that. So when you see this, note, by the way, that these are not ordered. There's no sense in which C comes before E, right? This is an equivalence class of motions in musical space. So it turns out that elementary tonal theory books are chock full of descriptions of voice leading, and they basically, the process of becoming a musician is a process of internalizing probably hundreds of very familiar paths from one point in musical space to another. Okay? So this is the simple idea that I'm going to be building the rest of the talk on. And what I want to do now is ask the question, what can you do once you've actually formalized and mathematized and made rigorous the concept of voice leading? And I want to give you 3 answers. Answer number 1 is you can count them. Answer number 2 is you can theorize about them. And answer number 3, which is the most mathematically interesting, is use them to define a genuine geometry of chords and chord types. There's a reason why I am putting this last, even though it's mathematically most interesting, because I mean, this is all very cool, but the geometries that I'm going to talk about make no sense unless you understand what their musical significance is, and to understand that, you really have to understand what a voice leading is. Okay, so how do you count voice leadings, and what the heck does this mean? Well, you assemble a large number of musical scores in some computer-readable format. One of the wonderful things in music over the last 10 years has been the development of a cross-platform XML representation for musical scores that different programs can read. So suddenly it is possible at a few clicks and a few Google searches, you can download 700 mass movements by Palestrina, every Mozart piano sonata, every Beethoven piano sonata. Giant portions of the classical music repertoire are now available, and your computer can read them, and different programs can throw them around to each other. However, in order to do the analog of linguistics on music, you can't just crunch the notes, unfortunately. Right now, you need to go through all of this music and analyze it by hand, and at every point say, what is the key that we are in, and what is the chord that we are listening to. And someday a computer will be able to do this, but the way that the computer is going to learn to do this is by doing machine learning or some kind of complicated rule-based algorithm and using these hand analyses as a ground truth to compare the efficacy of different methods. And then once you have these things, you do a lot of programming. And this slide is the story of my life over the last 4 years. Over the last 4 years, I have assembled a corpus of 1,000 musical pieces, 100,000, 120,000 musical scores, each hand annotated by me. So it's roughly the effort of writing a substantial novel. These scores go from Dufay, who was a composer in the 15th century. That's 1400, all the way to Brahms, and then there's a giant rock corpus that I also use. As you can see, I analyzed all of the Bach chorales, which is about 20,000 chords in the book. All of the Mozart piano sonatas, a third of the Beethoven sonatas, 7 Palestrina mass movements. So, and then a smaller amount of a lot of composers in between. Something like this represents 2 weeks' work. So what this allows us to do is, for the first time, do a kind of quantitative study of the evolution of all sorts of musical parameters, because for each of these, the computer not only knows the notes, but the meaning of the notes. And so one of the things you can do is actually theorize and answer questions about how do particular composers get from one musical place to another. In other words, you can assemble statistics on many different musical properties, one of which is voice leading. So I'm going to go through this very quickly, because this is really mostly interesting to musicians, and you guys just need to know the general idea. Here are 2 different ways of getting from what's called the 7/6 chord in C major to the tonic chord in C major. They sound like this. Okay, so this is a very common tonal progression. That's the one I played. You might ask, well, which of these is the right one? Do you usually go from here? Do you usually use this voice leading, or do you use that voice leading? Almost every textbook says, this is the right one, this is the wrong one. Okay, so these are textbooks that sell 10,000 copies a year, I mean maybe 50,000 copies a year, are presenting the instruction that this is bad and this is right. So if that's not true, there's a pretty big problem, and with my statistics, Bach says that the textbooks are wrong. Okay? So this is the one that Bach uses all the time, and this is the one that the textbooks tell you to do. Now, for someone like me, this is not a big problem in the era of global warming and terrorism and so on. But to me, it is a problem. You know, it's a problem when 50,000 undergraduates each year are being told something that is blatantly contradicted by the greatest, master of tonal counterpoint. And the reason it's blatantly contradicted is because these textbooks were written by people who had no access to statistical information, and so they just kind of made it up. All right, here's another one. Sorry, I can get a little bit hot under the collar about this. This one is really interesting. So the progression from a 4 chord to a 1 chord is one of the basic tonal progressions. Hallelujah. Okay? And again, the standard textbook theory, and pretty much everybody's story about this, is the way you get from here to here, from 4 to 1, is that the notes move down. And there's elaborate theories about just how important it is that these notes always move down. Of course, it's possible to do things like have the notes move up. So you could say, is the normal voice leading for getting from 4 to 1, should the notes move down? And this is connected to a whole metaphysical story about what this 4 chord is. And almost everybody says, yes, that's right. This is the correct one. The notes should always move down. And again, those 50,000 textbooks all say the same thing. The amazing thing here is that there is no right answer. If you look at the large statistical database and you count up all your voice leading vectors, this one is incredibly popular up through Bach, and then it gets annihilated and disappears in favor of this one. So there's a whole story about how composers like Corelli and Bach are speaking the same language as composers like Mozart and Beethoven. And that story seems not to be true. There are all these amazing quantifiable differences. And the prevalence of this particular voice leading is absolutely fascinating because, if I could just speak music for a second, it undercuts the notion that the 4 chord is fundamentally different from and in opposition to the 5 chord. This kind of vector that takes you from 4 to 1, has a leading tone in it and has a lot of the qualities of a 5 chord. And this is a huge, big part of how this chord was conceived, not just by Bach and Corelli and the Baroque masters, but by their predecessors, the Renaissance composers like Monteverdi. And so this is a huge way in which our normal way of doing music history and making a dividing line between the modality of the Renaissance and the functional harmony of the Baroque, it just seems like it's not right. And there are all sorts of ways in which composers like Bach and Corelli naturally group with earlier composers. So I just present these. This is the kind of thing that music nerds like me really get interested in.
What's the 1 chord? I don't understand why there are 2 different versions of the 1 chord.
Well, because they're different voice leadings. So they're the same notes. I started with the same F chord, and so if I have 2 different voice leadings, I'm going to end with different 1 chords. I could have ended with the same 1 chord, but then I would have had to start with different 4 chords. Remember, these voice leadings are different vectors, different ways of getting from one point to another, and so typically that means that it's not always true, but no, it is always true, that if you start with the same 4 chord, 2 different vectors that both take you to the 1 chord are going to actually take you to slightly different representations.
These general chords are just a collection of 3 or 4 notes on the 12-tone circle. So if you've got different representations of those notes,
yeah,
it's still the same chord.
Right. These project down to the same points on the circle, but they lift to different points in the tone space. Right? That's what and the trick about doing all this is we have to think in both of these spaces at the same time. Anyway, so music nerds get really excited, at least I get really excited. The thing is, now I can teach my students, now that I have a formal description of musical vectors, I can actually give my students accurate information about this stuff, which turns out to be not an unalloyed pedagogical blessing, because I'm always telling my students, well, here's what the textbooks say, and it's very simple, and the reality is incredibly complicated, and there's a slight different story about Bach and Mozart. And I do notice that their eyes tend to glaze over and they get a little confused. And they might like the simple story better, but it's wrong. Okay, now let's do something more interesting. Let's start theorizing about voice leadings. Before we get to any geometry, let's start just doing, now we're moving into the place where music nerd and math nerd maybe overlap a tiny bit. And we can think about voice leadings that are structurally interesting in some way. We just have this simple tool about a voice leading. And an iterable voice leading, I call it, is a voice leading that can be repeatedly applied to produce a structure that is harmonically interesting, meaning the vertical chords are going to be related in interesting ways, and melodically interesting, meaning the melodies produced by iterating this voice leading over and over and over again are going to be interesting, meaning they're going to do something we care about musically. And now I'm going to give you 2 examples of this that hopefully will stoke a little bit of mathematical interest. One of them is what I call a canonic voice leading, a voice leading that produces a canon. A canon is like a round, row, row, row your boat, the same melody laid on top of itself multiple times to produce harmonies that are pleasing. And then there are these things called oblique voice leadings, which are kind of musical impossibility or something that shouldn't really happen. So this idea that a voice leading makes a canon is a little paradoxical because a voice leading just is something that happens instantaneously. That's a voice leading. And a canon is something that stretches through time. So let me show you about these things. A canonic voice leading is a voice leading that connects 2 chords that musicians call transpositionally related. That means they project down to a set of points on the circle that are related by rotation. That means they sound similar. So major chords are all transpositionally related. They're all related by rotation on the pitch class circle. Okay, so this chord, this is an A major chord with 2 instances of the third. and this is an E major chord, also with 2 instances of the third, and so they're the same kind of chord, and that's the first qualification for being a canonical voice leading. The second thing is that the voice leading has to act as a cycle on the voices, meaning we have to be able to number these voices or name them somehow, numbered 1, 2, 3, 4, and now we number their analogs over here, and there are 2 different ways of doing it, one right, one wrong, and the right way creates a cycle where 1 gets